Okay, everybody. So, figuring out the error in our Taylor approximations. So here's what we're going to do. What we're going to do is, remember we have, for a function f of x at some base point a, the nth order Taylor polynomial is the sum from k equals 0 to infinity, no, n, so the kth derivative at the base point divided by k factorial times x minus a to the k, right? And our hope is that as n goes to infinity, the nth Taylor polynomial goes to the function itself. And I said that this isn't always the case, but sometimes it is. So how to figure out when? Well, what we need to do is figure out what is the difference. We need to somehow understand something about the difference between these two. So what we're going to do is define a function r sub n of x, which we will call the remainder, the Taylor remainder, which is just the difference between these two. So it's going to be f of x minus t sub. Actually, let's do this the other way around. It doesn't really matter which way we put these. So the nth Taylor polynomial minus the function itself. Okay, and what we need to do is we need to understand what does this function do as n goes to infinity. And this is a hard question, so this is going to take some time. Okay, this is going to take some time to figure out. And there are a few facts that I want to make sure we understand before we dive in. So the first fact is that for a function g of b minus g of a is equal to the integral from a to b of the derivative of g dx. This is essentially just the fundamental theorem of calculus, right? The fundamental theorem of calculus says, how do you evaluate a definite integral like this? Well, you find the antiderivative of this function, which, well, the antiderivative of g prime is g, and then you evaluate at the bounds and subtract, right? So this is just the fundamental theorem of calculus. The second fact is that the absolute value of the integral from a to b of g of x for any function g, so g can be any function here, this absolute value is less than or equal to the integral from a to b of the absolute value of g of x. Okay. Now graphically, this should be hopefully pretty clear because the thing on the left is the absolute value of the net area. When I say net area, remember an integral computes area, but area below the x-axis counts as negative, and so there might be some cancellation of area, and that's what I mean when I'm talking about net area. It's the area including that canceling, or allowing that canceling to happen. Okay, on the other hand, on the right-hand side here, we're counting all area as positive, right? Because we're taking the absolute value of the function itself, which, right, if g is a function that sometimes goes below the x-axis like this, from a to b, when we take an absolute value, that sort of flips the negative part up above, and then when you calculate an integral, all of your area counts as positive. So all this inequality is saying is that you get more area if all of it is positive than if you allow some of it to cancel. That's all this says, which is, when you phrase it that way, it seems kind of obvious. Okay, and then the last thing is about the relationship of Taylor polynomials for a function and the derivative of a function. So let's write down the nth Taylor polynomial of f, right? So this is going to be the sum from k equals 0 to n of the kth derivative of f at the base point over k factorial times x minus a to the k. Okay, so what I want to do is take the derivative of this just to see what happens. So when we take the derivative of this, right, first of all, the k equals 0 term, the k equals 0 term is a constant, right, because when k is 0, here we have x minus a to the 0, and that's 1. So the k equals 0 term is constant. So when we take a derivative, it goes away. So this sum now starts at k equals 1. Okay, and then we can take, because this is a big sum, we can take a derivative term by term in a sum. That's the sum rule for derivatives. And when we do take a derivative, well, the only part of this thing that has x in it is this part. So this thing out front is a constant multiple, so we can just copy that down. Kth derivative of f at the base point over k factorial, and then do the power rule on the stuff that's left. The k comes down, x minus a to the k minus 1. Okay, so let's simplify this a little. So k equals 1 to n. So this is the kth derivative of f, but that is the k minus first derivative of f prime, right? So here we're going to do k minus first derivative of f prime. If you count up all of the derivatives that are happening here, there's one derivative right there, and then there's k minus 1 derivatives right there, and so there's k derivatives total. So it's still the same k derivatives. I'm just splitting it up in a funny way for reasons you will see in a second. Okay. Now in the denominator, this k factorial is really k times k minus 1 factorial, right? So times x minus a to the k minus 1. Okay, and this is because k factorial, that's k times k minus 1 times k minus 2, and so on, all the way down to times 2 times 1. But look, this part right here, that's k minus 1 factorial, and then there's a times k out front. So I'm just breaking off the first piece of this k factorial and writing it out separately. And of course I'm doing that because now this k cancels that k. So what we have here is the sum from k equals 1 to n of f prime, the k minus first derivative of f prime, times a over k minus 1 factorial times x minus a to the k minus 1. Okay, so why did I do all this? One last thing that I want to do is I'm going to do a little change of counting variable here. So we'll rename our counting, let's use j for our counting variable, and j is going to be k minus 1. Okay, so if k starts at 1, that means j has to start at 0. And if k goes up to n, that means j has to go up to n minus 1. And then we have f prime, and then k minus 1, remember that's j. So this is jth derivative at a divided by, and now we have k minus 1 factorial, that's j factorial, times x minus a to the k minus 1, but k minus 1 is j. But look, this is a Taylor polynomial. This is the n minus first Taylor polynomial for f prime, right? Because of this prime right here, right? Okay, so the upshot of all of this is that the derivative, I don't know how to write this, the derivative of the nth Taylor polynomial for f is the n minus first Taylor polynomial for f prime. All right? So that's the final fact that we need to get the ball rolling. So our three facts that we need are for any function g, I guess it has to be differentiable. G of b minus g of a is the integral from a to b of the derivative of g. If we have an absolute value of an integral, we can move the absolute value inside at the expense of having an inequality here. And last thing is that the derivative of the nth Taylor polynomial for f is the n minus first Taylor polynomial for f prime. Okay, so now we're going to come back to this error function that tells us how far off is our nth Taylor polynomial. So remember, this remainder function is the nth Taylor polynomial minus the function itself. And what we're going to do, this is one of those situations where you kind of have to guess the result. So before you can guess the result, you have to do a couple examples so that you have a good guess. And then once you have a guess, you prove that your guess is correct. Okay, so we're going to do a couple examples, and so we'll do an example with n equals, I think, 1 and 2, or I guess 0. Actually, we're going to do, our two examples will be the n equals 0 case and the n equals 1 case. Then we will guess our error formula, and then we will prove that our formula is correct. Okay, so if you want to skip these examples and jump to the guess, I guess you have to see at least this first example just so that we know that our n equals 0 case is true. When we prove it, we'll use proof by induction. I'll explain that later, but part of that will be knowing that in advance that this n equals 0 case is true. So you're kind of on the hook for the n equals 0 case, I guess. Okay, so let's find the error function, or figure out how big the error could be for n equals 0. Okay, so we need to know how large could this error be. Well, just by definition, this error function is the 0th Taylor polynomial at x minus the function itself. Oh, sorry, part of this whole thing, we have to assume that the first derivative never gets larger than some fixed value. It doesn't matter what value it is, but we need some number that this never gets bigger than. So let's call that capital M. When I say never, what I mean here is on the interval from a to x. So for all the x values between a and x, the first derivative never gets bigger than this magic number m. How do we find that magic number m? That's somebody else's problem. We're going to assume that we have such a number. Okay? Of course, when we'll get into that later. Let me not say that now. Okay, so we have this difference, and what we can do is use our first fact. Our first fact says that this difference is equal to the integral from a to x of the derivative with respect to x of t sub 0 of x minus f of x. And I guess I need a dx and close my absolute value. Okay, so the reason that this is true is because this expression inside our absolute value, this is t sub 0 of x minus f of x. This is playing the role of our function g. Okay, minus, so now we need g, but at some other value. Well, we don't have anything else here, so what we need here has to be 0. So one thing that we know is 0 is t sub 0 at the base point minus f at the base point. Right? This difference is 0 because, remember, the 0th Taylor polynomial agrees with the 0th derivative of the Taylor polynomial agrees with the function at the base point. Right? This says that the Taylor polynomial goes through the base point. Right? That's why this is 0. Okay, so we have this function at x and at a, and so the difference is the same as the integral from a to x of the derivative of that function. All right, so that was fact number 1. Now we can use fact number 2 because we have an absolute value of an integral. So we can say that this is definitely less than or equal to the integral of the absolute value. Like so. Oh, while we're at it, let's compute this derivative. So derivative of t sub 0 of x dx minus derivative of f at x dx. Okay. Now for a special case. So this is a trick that's only going to work because we're in the n equals 0 case. Remember, the 0th Taylor polynomial is a constant. I tried to write an exclamation mark. The 0th Taylor polynomial is a constant. So right here, when we take a derivative of it, well, that derivative is 0. So that leaves us with, but then, once this part drops out because it's 0, this minus sign doesn't make a difference because we're inside an absolute value. So we're just left with the absolute value of the derivative of f with respect to x dx. All right. But remember, we assumed at the beginning that the derivative of f never gets larger than this magic number m. And I've been writing x here. I shouldn't be writing x because x is the upper bound. I should choose some other variable name. Let's call it t. Okay, so in this integral, all of the t values that this integral goes over are between a and x, right? And we assumed that this derivative never gets bigger than m for values between a and x. So that means that this absolute value inside is less than or equal to capital M. So now we're integrating a constant capital M from a to x, and that is m times t from a to x, and that is m times a minus x. Okay. So n equals 0 case, done. There is a bound for the error in the 0th Taylor polynomial. So here, the way I've written it, it actually does depend on a being bigger than x and not less than x. But if you do the calculation again with x being less than a, some minus signs show up, but then they're inside an absolute value, so everything works out okay. So the upshot is we need absolute values here. Okay, so that's the n equals 0 case. I am going to work out the n equals 1 case. So if you want to skip to the general guess, you can do that. But we're going to work through the n equals 1 case. And for the n equals 1 case, our magic number m is going to change. Okay, so this time we're going to assume that f double prime is not larger than m on the interval from a to x. And again, we're going to assume just for now that x is bigger than a. If x is less than a, you have to switch some things around and put in some minus signs, but it comes out the same in the end. Okay, so notice that our magic number m is a bound on the derivative that is one past the one we're working on, right? Okay, so now let's come up with a bound for the first, a bound for the error in the first Taylor polynomial. So this is, right, the first Taylor polynomial at x minus f at x. Okay. As with the n equals 0 case, I should have written these out in the n equals 0 case. The Taylor polynomial and the function agree at a, so we can stick t sub 1 at a minus f at a in here for free because this stuff just adds up to 0. Okay, and now again we can use the first fact, right? This is playing the role of g, and here we have g at x, and here's g at a. So we can replace this with the integral from a to x of the derivative with respect to x. There's a button on my mouse or on my pen, and if I accidentally click this button, bad things happen, and then I have to somehow make OneNote behave again. Okay, there. I think it's behaving now. Okay. So integral from a to x of derivative of x of our function g, which is, right, t sub 1 minus f dt. I can't use x because x shows up right here. Okay, close our absolute value. All right, now let's calculate this derivative. So absolute value of the integral from a to x of the derivative of t sub 1 with respect to x minus the derivative of f with respect to x dt. All right, and now we can use our second fact because we have an integral inside an absolute value. So this is less than or equal to the integral from a to x of the absolute value of the derivative of t1 minus the derivative of f. And now we finally have to use our third fact. We haven't used our third fact yet. Our third fact, if you remember, says that the derivative of t1 is the n equals 0 Taylor polynomial for f prime, right? So what we have here is the error, the order 0 error for f prime, right? But the n equals 0 case gave us an error bound for r sub 0, right? And it was m times x minus a with an absolute value. But sorry, and this should be a t, not an x. Uh-oh, it's freaking out again. Okay, so t minus a. Okay, and this is because, right, m is a bound for the first derivative of the function that we are working with the Taylor polynomial on, which is f prime, right? But m is a bound for f double prime. We assumed m was a bound for f double prime, which is the derivative of the first derivative. Okay, now that we have this simpler expression in here, we can actually do this integral. It's m over 2 times t minus a squared from a to x. And then when you plug in x and you plug in a, well, when you plug in a, you get 0 because of the a minus a thing. And when you plug in x, you get m over 2 times x minus a squared, right? And again, this was for positive, for a bigger than x. If you do the whole thing for a, sorry, I said that backwards. This is for x larger than a. If you do this whole thing again with x less than a, some minus signs show up along the way, but then you're taking absolute values, so it all comes out in the end, except we need absolute values here. So, same thing. All right. Now notice what has happened. For n equals 0, we got our magic number m times x minus a to the first power. For n equals 1, right, we had to do an integral along the way, and we got m over 2 times x minus a to the second power, right? So notice that this is one more than that, right? This power is one more than that power. And also notice that this denominator, well, it's not, this denominator, it's not clear what it should be, but you might guess, well, it's one more than the power. So is this n plus 1? That seems plausible at first, but, right, if we do this whole argument again, we're going to integrate again, and this squared is going to turn into a cube, and there's going to be a cube that shows up there. And so probably we should guess that this should be a factorial and not n plus 1. So here's our guess for what the general error should be. So our guess is that the error in the nth Taylor polynomial is no more than capital M over n plus 1 factorial, right? So this, but one bigger than that, and with a factorial, times the absolute value of x minus a, and then this power is 1 more than n, so n plus 1. And we have to say what capital M is. Capital M, so if we look at our derivatives, way up here, the derivative that m is a bound for is 1 more than the value of n that we're looking for, right? When n was 1, we needed a second derivative here. So since n is n here, we should have a bound on the n plus first derivative. So here we have to assume that the n plus first derivative of x gets no larger than m on the interval from a to x. Okay, so that's our guess. All right, now let's prove our guess. We already know it's true for n equals 0, right? Because we proved it earlier. So the idea for the rest of the proof is that we will assume that this thing is true for n minus 1 and prove that it is true for n. Okay. Now the big picture on why this, if we prove this, we're done. The big picture is that we know it's true for n equals 0. Okay. And what we're going to show is that if it's true, well, I just wrote it out again. What we're going to show is if it's true for n equals 1, then it's true for n. That means if it's true for one value, it must also be true for the next one. So we know it's true for 0. If we can prove this, then when we know it's true for 0, we'll know it's true for 1. But if we know it's true for 1, we'll know it's true for 2. And if it's true for 2, then we'll know it's true for 3, and so on. And that proves it for every value of n, every integer, right? So this is called mathematical induction. That's the fancy name for it. So we're going to assume that this error bound is true for n equals n minus 1, and we'll prove it's true for n. Okay. So when I say true for n equals n minus 1, what I really mean is for all functions. So we're going to assume it's true for all functions for n minus 1, and then we'll prove it's true for all functions for n. Okay. So what we need to do is let capital M be a bound for the n plus first derivative of f on the interval from a to x. Right? So since we're trying to prove our guess for n, we have to, our magic number m has to be a bound on the n plus first derivative. Okay. I'm sorry, my email is freaking out on me and giving me a bunch of pop-up notifications that are preventing me from writing. Oh, there's another one. Okay. So what we need to do is figure out how much error is there in the nth Taylor polynomial. So as before, so this is going to follow the same general outline as the previous cases. It's just everything is going to be a little bit harder because we have n's floating around everywhere. But otherwise, it looks pretty similar. So this is the nth Taylor polynomial at x minus the function at x. And while we're at it, we might as well stick in our t sub n at the base point minus f at the base point, because these add up to 0, right? So it doesn't hurt to throw those in here. Now we can use our first fact again. This stuff in this inside is our function g at x times g at a. So this is the integral from a to x of the derivative of our function g, and our function g is t sub n minus f. Okay, and this is integral dt. And again, I have to use t and not x because x is this variable out here. Close my absolute value. Okay, now let's calculate that derivative. Absolute value of the integral from a to x of the derivative of the nth Taylor polynomial of f dx minus the derivative of f dx, okay, all dt, close our absolute value. Now we can use our second fact. Our second fact was that when we move the absolute values inside an integral, we get this inequality. So integral from a to x, absolute value of derivative of the nth Taylor polynomial minus the derivative of f dx. And now we use our third fact. So our third fact, remember the third fact says that the derivative of t sub n is the n minus first Taylor polynomial for f prime, right? Okay. That means that here, this stuff is the difference between a Taylor polynomial and f prime. But that's what we called r sub n minus 1, right? This should be t. T? Yeah, t. And this should be t. Oh, this should be t. I'm a mess. Okay, so what is r sub n minus 1? We do have to be a little careful because this remainder, this is the error in the n minus first Taylor polynomial for f prime. This is not the remainder in the n minus first Taylor polynomial for f, but the one for f prime. Okay, but since this is an n minus first Taylor error, we have an error bound because we assumed that we know what it was for n minus 1, right? So we assumed that this was less than or equal to the integral from a to x. So we know that this error is no bigger than capital M over n minus 1. So, sorry, no, n. So m over n factorial times absolute value of x minus a to the n, right? And again, this shouldn't be x, this should be t. Okay, this was our assumption, right? We assumed that our error bound, our guess for the error bound was true for order n minus 1 Taylor polynomials. And this is what that guess is for n minus 1. Okay, now that we have it written like this, since x is bigger than a, t is bigger than a, and so this absolute value, we can actually put parentheses here. And when we have parentheses there, well, now we can do this antiderivative, or we can do this integral. We get m over n factorial times, and then do this antiderivative. It's 1 over n plus 1 times t minus a to the n plus 1 from a to x. Okay, now let's simplify this. M times 1 is m over n factorial times n plus 1. That's n plus 1 factorial. And then here we have, when we plug in a, we get 0. So let's just plug in x. We get x minus a to the n plus 1. And this was for x greater than a. For x less than a, again, some minus signs show up, but there are some absolute values, and everything comes out in the end. You just need absolute values here. Okay, so we've successfully showed that our error formula is true for n equals 0, and we know that if it's true for n minus 1, it's also true for n. And so this chain argument says that if it's true for, since it's true for 0, it's true for 1. Since it's true for 1, it's true for 2, and so on. And so our error formula works for every value of n. All right. One thing I didn't mention is that this m, it's right. The magic number m we need for this to use our assumption is that m is a bound on the n minus first derivative of f prime, but that's what it is because, we need to know that m is a bound on the nth derivative of f prime, but it is because m was a bound on the n plus first derivative of f, but these are the same thing. So that what m is also works out. Okay, So finally, we have this error bound, right? So m is a bound on the n plus first derivative on the interval from a to x. Then the error in the Taylor polynomial is no larger than capital M over n plus 1 factorial times absolute value of x minus a to the n plus 1. Okay, so deep breath, right? A pause, intermission. We have this Taylor error bound. Now we need to use it to see why our Taylor series for e to the x, sine x, and cosine x, why the Taylor series are equal to these functions. Okay. We'll get to this one later. Okay, let's deal with these. Okay. Now, what we want to show is that the limit as n goes to infinity of our Taylor error is 0, right? Because remember, r sub n is the nth Taylor polynomial at x minus the function at x. Well, if the limit of this, if we take a limit as n goes to infinity, right? Here we have the limit of r sub n. Here, the limit of t sub n is the full Taylor series. Right? So let me not write it out. The full Taylor series. And of course, this doesn't depend on n, so this is just f of x. Right? So if we can show that this limit is equal to 0, then the difference between the Taylor series and the function is also 0, and that means that they're equal to each other. Okay, so what we really want to show is that this goes to 0. All right, so let's first do this for e to the x. Okay, now for this whole thing, we're just going to fix x, right? Everything we did for estimating our error in our Taylor polynomial depends on fixing an x value. So let's fix an x. Let's calculate what is the n plus first derivative of f. Well, f is e to the x. When you take derivatives of it, you just get e to the x. Okay. How big can e to the x get? Remember, we need to choose this magic number m that is a bound for this n plus first derivative. Okay, so how big does this function get on the interval from a to x? Well, the biggest this gets, e to the x is an increasing function, so it's biggest at the right-hand endpoint of this interval. So that's e to the x. So we can just let m be e to the x. Well, actually, if x is less than a, then we're talking about the interval from x to a. Sorry, a is 0 in this case. Right, a is 0. I should write that. If x is less than 0, then we can take m to be e to the 0, right, which is 1. Right? So the upshot of all of this is that we should take m to be the maximum of either 1 or e to the x, whichever one is bigger. Right? Whichever one is bigger. Okay, so now let's write down our error bound. Our error bound, the error is less than or equal to the maximum of 1 and e to the x, whichever one is bigger, divided by n plus 1 factorial times x minus 0, right? Our base point is 0, x minus 0 to the n plus 1. Okay, now we want to take the limit as n goes to infinity. And we're hoping this is 0, right? But it's hard to tell. Here's how to tell what happens as n goes to infinity. So first of all, let's pull this maximum out to the front. Okay, and then we're going to pair up these terms. So all of these x's, this is x times x times x, and so on times x. Right? There are n plus 1 copies of x here. Okay, now what is hiding in this factorial? Well, there's an n plus 1, and there's an n, and so on, down to a 1 and a 2 and a 3, right? There are, in the denominators, there are also n plus 1 things, all multiplied together in our denominators. So our denominators pair up with our numerators in this nice way, okay? Now, imagine what happens when n is large. When n is very large, it's much bigger than x, right? Remember, we fixed x at the very beginning. So when n is large, it's much bigger than x. In particular, much bigger than the absolute value of x, right? So, right, we have all these numbers, x over 1, don't forget this maximum out here. Maximum of 1 and e to the x. So times x over 1 times x over 2 times, and so on. At some point, you get to this, the first integer, we get the first one bigger than x. Right, so let's, whatever number that is, let's say it's capital N. Okay, and then there are all the ones after that. X over n plus 1 times x over n plus 2 times x over n plus 3, and so on, all the way out to x over n, whatever x over whatever little n is. Okay, now the key thing is that all of these are all smaller than 1. And when n is much, much larger than x, many of these are much smaller than 1. And as n goes to infinity, we're multiplying by more and more numbers that are much smaller than 1. And so this has to go to 0. So this whole thing goes to 0. But remember, that means that this error goes to 0. So what we just showed is that this error goes to 0 for x. Right. So the Taylor polynomial is for e to the x is equal to e to the x for our fixed x value. But, I mean, our argument didn't actually depend on any particular value of x. All that mattered was that x was a fixed value. So this is true for a single x value, but it's also true for any other x value, right? So that means that these two are equal for every x value. So, right, we can add every. All right, so we were able to prove using our Taylor error bound that the error for the error in the Taylor polynomial for e to the x went to 0. So that means the Taylor series is equal to e to the x. Okay. That one was kind of hard because we had to work out this limit. The one for sine and cosine are easy, actually. So let's do sine. You can do cosine because it's almost exactly the same. So let's do f of x equals sine. Okay. We need to figure out how big can the nth error be. And remember, we need this magic number m to figure out how big this error could be. Well, the n plus first derivative of our function is one of these four functions, plus or minus sine x and plus or minus cosine x, right? Every derivative of sine is one of these four functions, but the absolute value of every one of these four functions never gets bigger than 1. So we can just take 1 for our magic number m. So our error bound for the nth error is 1 over n plus 1 times x minus the base point, which is 0, to the n plus 1. And now we're left with exactly the same kind of limit that we just wrestled with for e to the x, right? So now we need to take the limit as n goes to 0. We already know that this limit goes to 0. So we're done again. So the Taylor series for sine at the base point 0 is equal to sine. Equal to sine x. Okay. you can see that this would work out for cosine. The only thing that's different for cosine is which derivative is which. But right, how we chose m didn't actually depend on which derivative was which, so this whole argument goes through the same for cosine. Okay, so at this point we know that e to the x is equal to its Taylor series. We know that sine x is equal to its Taylor series. We know that cosine x is equal to its Taylor series. That leaves one function, one of the big four Taylor series, which is this, 1 over 1 minus x. Remember the Taylor series for this, we don't know that it's equal yet, the Taylor series for this was the sum as k goes from 0 to infinity of x to the k. All right, and if you try to use the Taylor error bound to figure out what is going on with this sum, it's possible, but it's kind of annoying. And there's a nicer way to get around to it, which is using an algebra trick that you should know. Okay, you should know this algebra trick, and the algebra trick is to factor 1 minus x to the n. Okay, now 1 minus x to the n, it turns out it factors as 1 minus x times 1 plus x squared, and so on, all the way up to x to the n minus 1. So why are these equal? Well, just multiply this all out. When you do 1 times each one of these things, you get 1 plus x plus and so on up to x to the n minus 1. And then when you do x times each one of these things, you get minus x squared, and so on, minus x to the n minus 1. And then for the last one, you get minus x times x to the n minus 1, so that's minus x to the n. And then when you add all of these things up, well, this 1 doesn't cancel, everything in the middle cancels, and then this minus x to the n doesn't cancel. So when you multiply all this stuff out, you get this. So that's why it factors. Right? We guessed that it factored, and then we proved our guess was correct by multiplying it back out. Okay, well, now that we know that these two polynomials are equal, we can divide both sides by 1 minus x. So I'm going to divide this by 1 minus x and divide this by 1 minus x. Well, on the right-hand side, these cancel. So now we have 1 minus x to the n over 1 minus x equals 1 plus x plus and so on plus x to the n minus 1. Notice that this is the sum from k equals 0 to n minus 1 of x to the k. All right, so now these two are equal to each other, so if we take the limit as n goes to infinity, both of these should be equal to each other. Both limits should be equal to each other if both limits exist. So I'm going to write equals, but keep in mind that these are only equal to each other if both limits exist. And when I say exist, I mean exist and are finite. Okay, so on the right, what do we get when we take the limit as n goes to infinity? So sum from k equals 0 to n minus 1, x to the k. So on the right, this limit is, well, it's the sum from k equals 0 to infinity of x to the k, right? That's the Taylor series that we were working with. Now let's take the limit of the stuff on the left. Here we have to be a little careful, right? If the absolute value of x is less than 1, right, then, well, the only part that depends on n is this part right here. So we can do 1 minus the limit as n goes to infinity of x to the n over 1 minus x. Okay, well, if the absolute value of x is less than 1, then when you raise something less than 1 to larger and larger powers, it goes to 0. Right? That's true for anything between minus 1 and 1. So in this special case, this limit becomes 1 minus 0 over 1 minus x. But 1 minus 0 is 1, of course. Okay, so remember we said if these limits exist and are finite, then these two things are equal. Well, this limit exists if the absolute value of x is less than 1. So these are equal if the absolute value of x is less than 1. Okay. Now, if the absolute value of x is greater than or equal to 1, well, this limit, I guess, this only exists for x from minus 1 to 1, including 1, but this limit only exists, this limit only exists for x values from minus 1 to 1, not including 1, right? So, yeah, I mean, if you look, this x can't be equal to 1 here anyway, so we want to exclude x equals 1. So, so this argument that we use, it fails spectacularly if the absolute value of x is greater than or equal to 1, because these things blow up to infinity or jump around too much, right? If x is negative, then every number that we're adding here switches the sign and things go crazy. But if the absolute value of x is less than 1, then this is equal to this. And that finally proves the big 4. I don't know how long this video was, but it was pretty long, so if you stuck with it, congratulations. That's it.